In this chapter, let's discuss the energy, heat, and work of thermodynamic systems. A thermodynamic system is a system with a large number of particles, and the system occupies a macroscopic space. Suppose we have a ruler in logarithm scale. Atoms and molecules are smaller than the scale of nanometer. They are microscopic systems. The systems from nanometer to micrometer are mesoscopic systems. Viruses are typical mesoscopic systems. Systems bigger than 1 micrometer are considered to be macroscopic systems. Cells, insects, and mammals are all macroscopic systems. Thermodynamic systems are macroscopic systems. The state of a particle in three-dimensional space has 6 parameters. There are 3 parameters for its position and 3 parameters for its momentum. Thus, the state of a system with n particles has 6 n parameters. The state described by all 6 n parameters is a microstate. In a thermodynamic system, the positions and momenta of all the particle change with time. So, the microstate of a system changes all the time. It's obviously impossible to study the system by analyzing its microstates. The macrostate of a system is described by its macroscopic properties. The macroscopic properties of a system are the results of the collective behaviors of all the particles. The macroscopic quantities of thermodynamic systems are called state functions. Typical state functions are pressure, volume, temperature, etc. A macrostate corresponds to a number of state functions. Since particles exist in a system, energy and mass are distributed in the system. A system is in internal thermodynamic equilibrium if there is no macroscopic energy or mass flow within it. For example, a bottle of steady water is in thermodynamic equilibrium. A pot of boiling water is not in thermodynamic equilibrium. Two systems are in thermodynamic equilibrium if there is no macroscopic heat or mass flow between them, even if they are connected by walls permeable to matter and energy. For example, steady water and oil in a glass at the same temperature are in thermodynamic equilibrium. If there is no macroscopic energy flow between two systems, they are in thermal equilibrium. The zeroth law of thermodynamics states that, if two systems are each in thermal equilibrium with a third, then they are in thermal equilibrium with each other. The zeroth law of thermodynamics can be understood in such a way. If system A and B have the same temperature, meanwhile, system B and C have the same temperature, then system A and C have the same temperature. For example, water, ice, and water vapor at the triple point are in thermal equilibrium with each other. Systems in thermodynamic equilibrium are always in thermal equilibrium. If the macrostate of a system, that is, all the state functions, does not change with time, the system is in a steady state. The systems discussed in general chemistry are almost in steady or quasistatic states, which change very slowly, so that they always remain in internal thermodynamic equilibrium. The change of a state function is the difference between it at the final state and at the initial state. In other words, the change of a state function is independent of the pathway. On the other hand, if the change of a quantity is independent of the pathway, it is a state function. If the change of a quantity is dependent on the pathway, it is not a state function. In thermodynamics, the universe means everything. The surroundings of the system is everything in the universe except those in the system. The systems can be categorized based on whether they exchange mass or energy with their surroundings. If a system exchanges neither mass nor energy with its surroundings, it is an isolated system. Especially, the universe is an isolated system. If a system exchanges energy but does not change mass with its surroundings, it is a closed system. If a system exchanges both mass and energy with its surroundings, it is an open system. In general chemistry, the systems we discuss most frequently are closed systems. For example, the water in a closed thermos bottle can be regarded as an isolated system. A leaded transparent flux can be regarded as a closed system. A living cell can be regarded as an open system.